look at our first practice exam problem for exam 2. So basically integration by parts, why not use Mathematica for CFT? And we're going to do just that today. So continuous Fourier transform problem, calculate first 6 harmonics of the above signal using CFT, plot the frequency spectrum. What's the dominant frequency? What's the fundamental frequency? What's the maximum frequency? So we can answer some of these questions right now. So this signal is aperiodic, increases, decreases, and it seems like our period t is equal to 35 times 10 to the minus 6 seconds. So thus our delta f is going to be equal to 1 over t. And let's go ahead and calculate that out right now. Use Mathematica. Go ahead and put this over here. Let's see if I can actually keep it over here on this side. So my t is equal to, let me quit my kernel right here. So t equals 35 times 10 to the minus 6. Here we go. And then I know that my delta f, actually just did it, delta f equals 1 divided by t. Let's go ahead and kind of look at that numerically, look at this numerically. So this is my delta f, so my fundamental frequency. We are asked to calculate the first 6 harmonics, including our nil frequency. So we know that 6 times delta f will be my maximum frequency, so that's my f max. And dominant frequency we're going to have to figure out. So I've already kind of answered most of this question. So let's go ahead and figure out and plot the first 6 harmonic coefficients and figure out our frequency spectrum. So what I'm going to do here is I'm going to look at my points that I'm being given. Are, let's see, at a time of 0 seconds, I have a value of 5. At a time of 5 times 10 to the minus 6, I have a value right here of 15. At a time value of 15 times 10 to the minus 6, I have a value of minus 10. And at a time value of 20 times 10 to the minus 6, I have a value of 5. And finally, at a time value of basically 35 times 10 to the minus 6, I have a value of 5 as again. So these are kind of the values that I have. Let's double check. So 0, 5. Let's look at this numerically. At 5 microseconds, we're 15. At 15 microseconds, we're minus 10. At 20 microseconds, we are 5, and then sort of 5 again. So let's go ahead and figure out to calculate our harmonic coefficients. So to do that, we're going to have to do a sub n equals 2 over t, and we're going to have to integrate all these functions. So I need to integrate my, basically, well, first I actually need to find my y functions. So I'm going to fit this data. So I'm going to look at fit, for example, data 1, data 2, right here, and we're going to fit it as a function of t. So we'll fit that right there. That's our first function. And I'm going to do a table. I go from I goes from I plus 1, and I'm going to go from 1 to length of my data, but that's not going to work because I need to close actually. Because if I go to the length of my data, then I'm not going to have this, so I need to go to length of data minus 1. So there's my y functions. I should have 4 of them. So 1, 2, 3, 4. So fantastic. So functions, or my y functions. So there we go. So now I need to do integrate y functions 1, and I need to multiply that by cosine of 2 times pi times n times t divided by t. And I need to integrate that from t goes from my first data 1, 1. Again, that's just the first element here. So there from data from 2, 1, actually 1, 2, 2, 1. And there it is. So that is my kind of the first, that basically the first integral. So now I need to repeat this. So table. So I need to go now from I goes from I to I plus 1, and I need to go from basically from I from 1 to length of my y functions. There we go, and I need to total that because I'm adding those functions together, and then I'm just going to do this, copy, and put it right there. So that's going to be my a sub n function. So let's go ahead and check a sub n slash dot n goes to 1. Here's my first harmonic. So I can do table a sub n goes from I. We're looking at the first 6 harmonics from 1 to 6. There we go. I'm going to suppress this output right now because we've already done that. I want to make it look pretty. An elegant code, as Professor Carter would say. 3016. Basically, Mathematica coding for material scientists. So I can do the same thing. Now I just need to do sign. And there's that function I do here. There's my b sub n. And if I want to do my a sub naught, I know that my b sub n will be 0 because what is sine of 0? That's going to be 0. My a sub n is going to be a sub naught is going to be equal to this whole thing, except now I do not have my cosine terms and disappear. So that's my a sub naught. So you can include that. Again, that's the 0th order harmonic right there. But I want to plot my frequency spectrum, and I want to look at the dominant frequency. I'm going to be able to plot that. So I'm going to do my c sub n is going to equal table square root of my a sub n squared plus my b sub n squared. Actually, I'm going to do this as my ANs. This is my BNs. I'm actually going to do this. A sub n I squared plus my b sub n I squared square root. I'm going to go from, oops. Then I'm going to do from I from 1 to length of a sub n. Oops. Actually, let's do my a sub n's and b sub n's and here. That's much better. So there we go. And what about my frequencies? My f. So my x-axis. So f is going to be, or my f's is going to be my table of I times delta f from I goes from 1 to 6. So I'm going to transpose that. Transpose fs cn. I'm going to do list plot. And I can make it nice, but again, this is just an exam, so you don't have to make it super fancy. And let me make sure that I have all my plot range all. So we can see that what is my basically dominant frequency? It's going to be my fundamental frequency right here. It's pretty close here to the second harmonic here. And again, we're plotting to our maximum frequency, which is going to be this 1712 value, which is right here. So there's 6 times delta f. So that is your frequency spectrum, your dominant frequency, your fundamental frequency, and your maximum frequency. So now we're asked to figure out this last problem. So we've figured out dominant frequency. It's that maximum frequency. Your dominant frequency is also my fundamental frequency. And now I asked some undergraduates in my group to plot the Fourier series and to plot 22, 6, and 60 harmonics. Did they label them correctly? So we know that as we increase the order of harmonics, we should get a tighter fit. So this is the worst fit. It has the lowest number of harmonics. Okay, that looks good. You can still see there's some deviation between our Fourier series and our function, so that's good. And then here, you could just barely see that blue value, so you're good there. Now, will you see something like this in an exam? Probably not as easy. So what I would practice is, if you were given a plot like this, let's just say that there are three values. And this was 5, 10, and 5 again. So, and then this was frequency 1, 2, 3. If you were given Fourier series, so y Fourier series 1, if I gave you something like 5 times cosine of 4 pi t, that's 2 is equal to, let's say, square root of 5 plus times cosine of 2 pi t plus square root of 5 sine of 2 pi t. And you're given a final one, yfs equals 5 times sine of 2 pi t plus 10, these are same values here, 10 sine of t, making this up on the fly, plus 5 cosine of 6 pi t. Which of these Fourier series would match with this frequency spectrum? Well, from this frequency spectrum, I know that my delta f is equal to 1 hertz, and I know that my period equals 1 over delta f. So that's equal to 1 second. So now I can kind of look. All right, let's look at the order. How many harmonics do we have here? We have 1, 2, 3. So these are both at the same frequency. Well, first, actually, this is our frequency at omega. So omega equals 2 pi f. We're always looking for these integral values of delta f. So here our frequency, our fundamental frequency, or the first frequency that we have here, is a frequency of 2. So our fundamental frequency is not 2. This one's counted out automatically. Now our harmonic, basically the amplitude here of our harmonic coefficients, remember this is a sub n, so a of 1, b of 1 is equal to 0. So the magnitude of Cn, or C1, is equal to square root of A1 squared plus B1 squared. So 5 squared square root will give us the value of 5. Here we have the correct, basically the correct order of harmonics right here, but like here the fundamental frequency is going to be equal to 1. However, here this is our C sub 1 is going to be square root of 5 plus 5, so that's going to be square root of 10. That is not equal to 5. Additionally, our C sub 2 is equal to C sub 3, which is equal to 0. So those don't exist. So this one's out. And we're left with this one. So here, this is 1 hertz, 2 hertz, 3 hertz. Excellent. That makes sense here in terms of our delta F. And then also, this is our A sub 1 is equal to 0. Our B sub 1 is equal to 5. That matches. Here our B sub 2 equals 5, and our A sub 2 is equal to 0. So, or excuse me, it's not equal to 5, it's equal to 10. So that magnitude matches. So we're good to go there. So 10 squared square root. And then finally, for our third, here now our A sub 3 is equal to 5, and our B sub 3 is equal to 0, and it matches here. So be prepared to do a problem similar in that vein. Again, inverse problems. Looking at, instead of calculating a Fourier frequency spectrum, look at a Fourier frequency spectrum, look at a Fourier series, and see if you could kind of match which corresponds to which. So little tip for the upcoming exam, what you might expect. All right, I'll see you in the next example problem. Thanks. Let me know if you have any questions. I'd be happy to provide another example. And yeah, see you next time. Bye.